안녕하세요. 기말고사 발표회 프리옵틱스 과목을 수강 중인 황지은입니다. 지금부터 발표를 시작하겠습니다. This slide presents the problem we are analyzing, a Fraunhofer diffraction pattern generated by a rectangular aperture with a double slit structure embedded along the y direction. The intensity equation contains sinc squared terms in both x and y, and a cosine squared modulation in y due to the slit separation. Our goal is to extract and analyze the x and y axis cross sections from this 2D diffraction field. The constants provided are normalized spatial frequencies. X over lambda z is 10, y over lambda z is 1. And the slit separation delta over lambda z is 3 over 2. This configuration suggests narrow diffraction in x and wider diffraction with interference fringes in y. When y equals 0, the y-dependent terms reduce to constants, so we only observe the sinc squared 10x term, which is the typical single slit diffraction pattern with narrow y and high central peak. It decays rapidly with increasing x. For the y-axis cross-section, we see a sinc squared envelope from the slit width multiplied by a cosine squared function that introduces interference fringes. The fringe spacing is determined by the value of delta over lambda z, here being 2/3. We implemented the diffraction pattern using MATLAB. This code defines the spatial grid, constructs the intensity equation using sinc and cosine squared, and plots both the 2D pattern and the 1D cross sections along x and y. The figure shows the simulated result. On the left is the full 2D Fraunhofer diffraction pattern. In the middle, the x-axis cross-section reveals the expected sinc squared shape. On the right, the y-axis cross-section shows the interference fringes within a broad sinc envelope. This confirms the analytical predictions. Here, we visualize the same diffraction pattern as a 3D surface. The sharp central peak and interference ripples along y are clearly visible. This plot helps convey the shape and structure of the intensity distribution more intuitively. This slide shows how the fringe pattern changes as delta over lambda z varies from 0.5 to 2.0. With smaller delta, fringes become wider and more separated. As delta increases, fringes become denser. This illustrates how slit separation controls fringe spacing. This plot extracts intensity along the diagonal direction x equals y. It provides a combination of both x and y modulations, offering insight into the overall symmetry and modulation behavior of the diffraction pattern. Now we shift to the optical transfer function, or OTF. The OTF is the autocorrelation of the pupil function and reflects how spatial frequencies are transferred in an imaging system. We will compare clear apertures, center stop pupils, and epsilon limited cases. This slide shows the step-by-step construction of the optical transfer function when a central stop is placed inside a square pupil. Spatial frequency axis has been divided into 4 key regions. Each segment corresponds to a different stop in the OTF based on how much of the pupil overlaps when it is shifted. This figure represents a limiting case where the central stop is very small, specifically reached by epsilon on each side. This causes a sharp but narrow dip in the center of the OTF. The slope of the drop is much shallower than in the previous case. We see a sudden central dip, a slow decay outward, and a sharp recovery followed by a final decay to zero. This scenario shows how even a small center obscuration can significantly affect the system's ability to transmit low-frequency components. This figure now shows MATLAB simulated results based on the same textbook cases. The black line is the baseline triangular OTF for a clear pupil with no stop. The red curve represents the stepped OTF with a full-size center stop, and it follows the segmented profile discussed on slide 11. The blue curve shows the case of a small epsilon stop, which produced the central dip discussed on previous slide. By coding these models, we can explore how physical changes in the pupil affect the imaging system's frequency represents and validate our theoretical understanding using simulations. This MATLAB plot compares 3 OTFs. The black curve is for a full square pupil, a triangle function. The red dashed line represents a center obstruction. The blue dot line shows a case where the central stop is extremely small. As we can see, blocking the center degrades the low frequency response. This 3D mesh shows the 2D OTF of a clear square pupil. It's a product of 2 triangle functions, forming a pyramid-like structure. The symmetry and spatial bandwidth are clearly evident. This presentation helps connect pupil geometry to frequency response. This plot annotates the blocked OTF curve showing its four distinct slope segments. Each segment corresponds to a geometric shift between the clear and blocked areas of the aperture. It illustrates how central obstructions reduce mid-frequency transfer more than high-frequency ones. Here, we color the different slope regions to emphasize how the OTF drops in stops. This visual breakdown helps explain how the overlap area in the autocorrelation changes piecewise as frequency increases. This grayscale image shows the actual pupil function in the spatial domain. The large square represents the clear aperture, while the smaller square in the center in the stop. This is the function being autocorrelated to produce the OTF. Including this figure helps us connect the physical aperture shape to the frequency domain behavior. Moreover, by modifying the grayscale intensity within the pupil, such as applying a gradient or a soft apodization, we could simulate more advanced optical systems like Gaussian filtered pupils or variable transmission masks. This makes the spatial domain pupil function a flexible experimental starting point. Here, we compare the total area under each OTF curve, representing an amount of spatial frequency information transmitted. As expected, the clear pupil transfers the most, while the blocked and epsilon cases lose more and more low frequency content. Thank you for your attention and thanks for your listening.